Hello and welcome to our last section in our unit on circles, power theorems. Power theorems are all related to specific chords, secant lines, or tangents of circles, and we'll break them down. There are three of them that we need to know for purely simplicity's sake. We're just going to break it down by what the formula is based off of its diagram. So we're going to let's first draw a circle with two chords in it. So off to the right, we're going to have the center of the circle here. That's going to be a little irrelevant to the problem because we are only concerned about two chords. So if I draw two chords here, let's call this, well, it doesn't quite matter. I'm going to label each chord part. I'm going to call this A, which means this small part of it. And then this part, I'm going to name it B. For the other chord, I'm going to call this C for this section, for this part, and this part I'm going to name it D. And what we have here is what we call the chord power theorem. Chord. So if you recognize we have chords and we're actually working with segment lengths as opposed to angles, remember angles are referred to this angle which works with this arc and this arc. That is different than what the chord we're talking about today. So here we are talking about segments, okay? So if you want to put that here, I'll put this in pink, I guess, for segments. If you want to differentiate it, you don't have to. We have the chord power theorem. And what this states is theorem. What this states is the part times its other part to make the whole. So A plus B is the whole, right? It's going to be equal to, so when you multiply those two parts together, it's going to be equal to these two parts, when the product of these two parts. So C times D. And that's actually much better if I actually color coded this. Let's call this A times B, the part times the part of the same segment, or the same chord, is equal to the product of the other two parts for the other segment, or the other chord. So if you want to think about it as part times, let's just leave it at that. So here we have, let's give in some values. Let's say, for instance, A is unknown. Let's say D is equal to 4. B is going to be equal to 6. That, now that I look at it, this absolutely 100% looks like a 6. That's supposed to be a B as in boy. And C is going to be 3. So if we use this formula, we could say, well, A is unknown, but we know B. B is 6. So I'm going to put a 6 here in parentheses. C is 3. D is 4. And then we could solve for the missing piece. So this is going to be 6A is equal to 12. Divide both sides by 6, and A is equal to 2. Okay, so we know that that part of the segment is going to be equal to 2. Now, so that's chord. Now we have two more. What else what other situations do we have besides chord? Well, we could also talk about an intersection that is outside of the circle. So here we have an intersection that is outside of the circle. Or inside of the circle. Let's talk about one that is outside. There are two different versions of them that we need to talk about. Secant, tangent. So if we have a secant tangent power theorem, that is exactly what it sounds like. We have a circle, so let's draw a circle. Let's draw a tangent line. And then a secant line. And then I'm going to label this X. I'm going to label this one Y. I'm going to label this one Z. Okay, so here is so this one's a little bit trickier because if you notice here we had 4 different parts and we just multiplied the components accordingly, right? So here it's a little different. We only have 3 parts to this. So how do we navigate this? Well, in this particular case, let's highlight. Just organize this. I'm going to highlight the secant line blue. I'm going to highlight the tangent line red. And we're gonna say, let's label this, the whole, or I'm gonna say x squared, which is the tangent part, is going to be equal to the part of the secant, the outside part, times the whole. So this can be y multiplied with the whole, y plus z. So if you, underneath this, if you want to, you could put the whole tangent squared is going to be equal to the outer part multiplied with the whole secant. If you want to break it down this way, you absolutely could. Some people just memorize it for what it is, but this is the whole secant segment, okay? And this is how you would solve for a problem like this. So in pink, I'm going to do this. You could actually, I'm going to say z is equal to 5, y is equal to 3, and x is our unknown. Solve for x. So here, I'm going to translate this. We don't know what x is, so it's going to be x squared. We know y is 3, so that's the outer part, outside part, times the whole. The whole is 3 plus 5. And we can just add those together. 3 times 8, which is 24. X squared is equal to 24. Root both sides. And you break this down. 4 goes into it perfectly, so we'll have 2 root 6. All right. Last one. Now notice the intersection was on the outside, and this was a secant tangent. The last one that we would talk about would be not tangent, because we've already talked about tangent. Tangent means that those two, if they intersected, these two would be congruent, so we already talked about that one. Would be secant. So the secant power theorem. All right, let's draw another circle. And I might need a little more space off to the right. Just make this smaller. And let's draw 2 secant lines where the intersection is on the outside. All right, now notice that we have 4 parts again. So I'm going to call this K, let's call this J, let's call this M, let's call this N. And the intersection is outside of the circle. Okay, so all of these K, J, M, and N refer to segment lengths. In this particular case, let's color code this again. One secant line I'm going to do red, the other secant line I'm going to do blue to just organize this information. And here we have, we're going to do the part times the whole. Okay, the outer part. So once again, it's the outer part. So let's do in red first, J multiplied with the whole, J plus K, is going to be equal to the outer part, which is M, multiplied with the whole secant, M plus N. Okay? Underneath this, you want to write outer part times the whole is equal to the outer part times the whole, specifically to the same coordinating pieces or coordinating secants. So let's fill in some values for K, J, M, and then solve for N. So let's see here. K, let's say, is equal to 8. J will be 6. M will be 7. Let's solve for N. All right, so J. So following this exact formula, J is 6. So we can do 6 times 6 plus 8 is equal to the outer part, 7, multiplied with 7 plus N. So we could do this a couple ways. Add these two up, we get 14. 14 times 6, we end up getting 84. And then here, we could distribute or we could weight. Either way works. It's really about personal preference at this point. So I'm going to distribute this just to make this a little bit universal. 49 plus 7n. Minus 49. You get 35 is equal to 7n. Divide by 7, divide by 7. And n here is going to be equal to 5. Now, it will not always work out this cleanly. More often than not, you will probably get some kind of fraction or decimal. I just chose numbers that I knew would work out, but this is the entire process. You could technically, if you really wanted to, divide by 7 here and divide by 7. And then you would get 14. Nope, 12, sorry. And then you would subtract 7. This 7, and you would get 5. So you could do it either way, but that may lead to fractions earlier on. So if distributing is probably more so recommended if you want to avoid the fractions, but it's just a personal preference at that point. All right, so these are our 3 power theorems: chord, secant, tangent, and secant, secant. If you do have any questions, please let me know, and I will see you in the next one. Bye.